Good afternoon and welcome to the Society of Wetland Scientists February 2019 webinar, where we'll be learning about valley bottom Palmiet Wetlands, the mysterious peatlands at the tip of southern Africa. My name is Kim Ponzio and I'm going to be your moderator today. I am the chair of the SWS webinar committee. And before we get started, I kind of wanted to go over some of the housekeeping items for using GoToWebinar. The general format for today's webinar would be a 45-minute presentation by our speaker, followed by approximately 15 minutes for questions. So at any time during the webinar, you can go ahead and type in questions in the questions pane, as you see in the middle of that slide, and I will pose the questions to the presenter at the end of the presentation. Also, you can go to the handouts pane and you will find a PDF of the PowerPoint presentation there. And you can adjust your audio for either computer audio or phone call. The webinar is being recorded today, and you'll receive a link to that recording following the webinar. And we also ask that you take a moment to complete the evaluation survey at the end, and that'll help us to plan for future events. You also, if you got practice doing twittering during our SWS Twitter Symposium in October and you're tech savvy, we ask you to tweet about today's webinar at #SWSwebinar. So we're proud to announce today that we have this webinar is pre-approved by the SWS Professional Certification Program. And so therefore it's applicable to continuing education credits, and that can be applied to your professional wetland scientist certification or renewal. You can get the participation certificates through an automated process now. You will receive an email from Michelle Chosek, our SWS Managing Director, about a day afterwards. And you want to check your spam email if you don't see it, because sometimes it'll go there. And to access the certificate, members log into the SWS store. And once you're logged in, you will see the certificate access item that can be purchased for $0 because these are complimentary for members only. You can also watch the webinar recordings on our past webinars page. So with the logistics out of the way, I'd like to go ahead and introduce our speaker. Today our speaker is Dr. Alana Rebello of the Conservation Ecology Department, Stellenbosch University, South Africa. She's currently a postdoctoral researcher in the Conservation Ecology Department, and her primary field is wetland ecology, though she is a generalist with many research interests, including wetland biogeochemistry, the ecological applications of remote sensing, the impacts of invasive alien plants, particularly trees, on the water cycle and biodiversity, and the benefits to society of intact or restored wetland ecosystem or ecosystem services. Currently, Alana is part of a large transdisciplinary team investigating the socio-economic benefits of investing in ecological infrastructure related to water security in South Africa. So with that introduction, I'd like to turn control over to Alana.
Good day, everyone. Thanks, Kim. It's really an honor to be speaking to you today, and thank you for tuning in and taking the time to learn a little bit about South African wetland systems. So while I just wait for the slide to advance, peatlands in the southeastern part of South Africa are rare, and yet despite seemingly unconducive conditions for peat formation, they do exist in this region. Most notable are Palmiet Wetlands. So by way of introduction, Palmiet Wetlands are classified as unchanneled valley bottom wetlands according to the South African Wetland Classification System, where wetlands are grouped according to their hydrogeomorphic type. For example, we have seeps, depressions, floodplain wetlands, and here is the location of a hypothetical valley bottom wetland. Valley bottom wetlands are often located in relatively steep valleys, highly connected to the fluvial system. They are characterized by diffuse flow through the wetland, and water may enter from a channel or by overland flow. Groundwater inflow may or may not be present in these systems. So Palmiet wetlands are distributed throughout the Cape Floristic region of South Africa. So this map shows the world's biodiversity hotspots. And here, represented by this yellow star, is the Cape Floristic region, known for its remarkable fynbos diversity. This map shows the location of this Cape Floristic region in Africa, and also a close-up where it is located in South Africa. These are some pictures of the folded sandstone mountains that characterize this region, the mountains of the Cape supergroup. So the Cape Fold Mountains form a series of parallel ranges that run along the southwestern and southern coastlines of South Africa for about 850 kilometers. You can see the mountain ranges in this light yellow color over here. And this is a picture of the folded sandstone that characterizes these mountain ranges. So the Cape Floristic region has a predominantly Mediterranean type climate, characterized by summer drought and winter rainfall resulting from the passage of cold fronts. The mean annual rainfall for South Africa is about 460 millimeters, and in the Western Cape is as low as 300 millimeters, with the mean annual APAN potential evaporation of around 2,000 millimeters. Yet surprisingly, we do get peatlands in this region. Fynbos ecosystems are also fire adapted, much like the Californian Mediterranean type climate systems. And we have issues in South Africa with alien trees from Europe and Australia, which increase our fuel loads, sometimes by up to 8 times. And fynbos is a shrub-dominated, relatively treeless ecosystem. So this has huge impacts on our fynbos ecosystem. Palmiet wetland soils and groundwater are naturally oligotrophic with a low pH, largely due to the soils of the Cape Floristic region being mainly highly leached dystrophic lithosols associated with the sandstone mountains of the Cape supergroup. As a result of occupying valley bottoms, palmiet wetlands tend to be long and narrow, so they're around 300 meters across or wide, and they're sparsely distributed across the Cape Floristic region, with around 8 significant wetlands remaining across an area of about 1,000 kilometers. And despite their isolation, they're remarkably similar in their species composition. Palmiet wetlands are dominated by the wetland plant Palmiet, or Prionium serratum, which is a unique species taxonomically. Palmiet has been suggested to be an ecosystem engineer by some, cited to be the species that was able to stabilize these valley bottoms originally and allow sedimentation and eventually the formation of peat. Palmiet wetlands are located in high energy catchments subjected to regular flood events of high force, which would rip out any shallow-rooted species, and in fact often does. Palmiet, a deep-rooted clonal species, is highly adapted to this disturbance and is typically able to recover from the floods afterwards. Although these wetlands are dominated by this plant palmiet, there are other fynbos communities in these wetlands. So this is a picture of palmiet. In this picture, the one in this picture is about 3 to 5 meters high. So they're really large plants. And the graph on the right is work done by Erwin Sibin and others, which shows wetland communities in sclerophyllous wetland vegetation. So they've classified these the vegetation into different groupings, and several of these groupings occur in these palmiet wetlands. In South Africa, peatlands are classified as wetlands with organic soils constituting an average organic carbon content of 10% or more, occurring at a vertical distance of at least 20 centimeters. So just to show, these are pictures of palmiet wetlands. And palmiet wetlands have a soil organic carbon content of about 15% and soil organic matter content of around 25%. Here you can see some of the peats of palmiet wetlands where the soils become exposed due to gully erosion. In terms of their age, palmiet wetlands are relatively young, having been dated to be around 5,000 to 6,000 years old in a few cases. So with the arrival of Western agricultural practices around 300 years ago, the landscape of South Africa was to change dramatically with the removal of wetlands, the channelization of rivers, alteration of the natural fire regime, and introduction of invasive alien trees. These changes were to alter the functioning and structure of many wetland systems in South Africa. So in the rest of today's talk, I'd like to cover how Palmiet wetlands compare with other peatlands globally, what is known about the structure and functioning of Palmiet wetlands, how this has changed with degradation, and just to end with an overview of restoration and rehabilitation interventions that we use on Palmiet wetlands. And I'll wrap up with some brief concluding remarks. So just to start, I would like to, on this topic of comparing Palmiet wetlands with other peatlands, I would like to thank my colleague Willem Emsens for his helpful ideas on how best to show how Palmiet wetlands compare to other peatlands globally, or more importantly, how they differ. So for this graph, I used his peatland dataset, as well as some data from Professor Rudy van Dichelen of Antwerp University, and a few data points from the literature. And the data are from peatlands from Sweden, the USA, Belgium, the Netherlands, Poland, France, and South Africa. I collected data from the literature on their pH, their nutrient status, and I classified this categorically into oligotrophic, mesotrophic, oligomeso, and mesoeutro. Their dominant vegetation type, and here we had about 15 types, for example, sphagnum or brown moss dominated or vascular plant dominated, and various combinations of these. I also recorded winter dieback, so whether there was dieback or not, or whether there was some dieback, and also peat depth. And I did a very quick unconstrained PCA in Kanoko for categorical and continuous data. And so this is just a very quick and dirty analysis just to give an idea of how these Palmiet wetlands relate to your northern hemisphere systems. So the first thing you'll probably notice is the very low explained variation on both the axes. So probably if better continuous data was collected, we'd get a nicer ordination. But for now, I think that it already brings some context and some perspective to how these Palmiet wetlands fit in. So at the top right of this graph, there's a sort of clustering, and I've just grouped this loosely here and called this, let me see if I can move this panel out the way. So I've called this valley bottom and poor fens, and this grouping includes almost all the Palmiet wetlands that I put into this data set, as well as one poor fen. This grouping at the bottom over here is mainly raised bogs. Okay, the slides are not advancing, so I'll just wait a minute and see if anything happens. There we go. So at the bottom we have a grouping of bogs. We have a big group of fens, and then another group sort of in between fens and the valley bottom wetlands. And I'll talk about that in a minute. So these are the kind of main clusterings on this graph with this data set. And firstly, what you'll probably notice is that because of the pH that was entered into this ordination, you find quite a strong grouping based on whether the systems are rainfall fed, groundwater fed, or sort of a combination of these. So in terms of the predictors, you can see there's pH, so high pH associated with fens, and that's obviously due to their groundwater link. And the first thing you'd probably notice about the Palmiet wetlands is that they occur over quite a range, and this is probably because they are variably connected to groundwater. Some are, some aren't. Sometimes in certain seasons they may be. And then just to look at a couple of the outliers, this one bog that doesn't really fit in is a short pocosin. The poor fen that groups with the Palmiet wetlands is a tall pocosin. The fen that doesn't fit into any of the groups is a gum swamp. And then this strange grouping of fens is from Sweden. It's from all over. So that's not why they're grouping separately. The main reason is because these are the slightly more rich fens, the oligomeso fens. The ones in the purple grouping are mostly oligotrophic. So I'll just put the rest of the predictors up. Another important factor was vegetation dieback. In bogs and fens, there tended to be quite high vegetation dieback, whereas in palmate wetlands, this was not the case. In terms of eutrophic or trophic status, bogs are typically oligotrophic. The fens in this grouping are the mesotrophic fens, whereas these are the oligomeso fens, and palmate wetlands tend to be also slightly more oligomeso. And then in terms of the vegetation dominating these systems, bogs obviously associated with sphagnum, fens with brown moss, and palmate systems are characterized by tall vascular species, which do not die back. Okay, so just showing the star showing this is how palmate wetlands fit into your northern peatland systems through this very quick analysis, and hopefully that brings some perspective as I continue with the presentation as to how relevant this is or how different it is from your systems. So just to also mention that there are many caveats to this analysis. It wasn't meant to be very detailed, just a very quick example of how this fits in. On the next slide, for the more visual people, I have a video clip which will play in a minute. And this is just to show or to bring palmate wetlands to life a little bit, to show what it's like to walk through a palmate wetland. So in this clip, which hopefully will play soon, the vegetation stands about 2 to 3 meters tall or higher. And as you move through the wetland to do field work, you tend to actually move over the plants, not through them. So hopefully that would give you a bit of an idea of what it's like to work in these systems and what these systems look like. We're typically moving through the system about 1 meter from the ground. Sometimes there's water flowing above the surface of the ground. Sometimes it's just dry soil, but it's an absolutely fascinating system to work in. So the next part of this talk today is what is known about the structure and functioning of palmate wetlands. And I'd like to start off on the geomorphological context, which is not my own research. It's research of other people, but it's nevertheless incredibly important in forming our understanding of these systems. So the best theory that we currently have for palmate wetland formation in these steep slopes or in these steep valley bottoms is when gully, cut and fill cycles laterally plane valley bottoms and contribute to valley widening and longitudinal slope reduction. So what are gullies? This diagram shows the erosion of a head cut, and this head cut eventually eats back through the system, forming a gully or a channel through the peat, or even through the bedrock, or down to bedrock. So here we have less erodible strata on the top surface, we have more erodible strata underneath, and as water moves over the structure, it erodes and eats away underneath the less erodible strata. And eventually there's a failure of this upper layer, and the nick point moves back, and the gully erodes upstream. So this is a very common process in palmate wetlands, and the theory is that this was actually a natural part of palmate wetland systems. And that over geological time, this process has shaped these systems and actually allowed palmate wetlands to exist where they do. So the second conceptual diagram that I have up on the left shows a cross section through a valley, and then on the right is the longitudinal section. And here we have a V-shaped valley bottom, which is what you'd expect in these systems. And the palmate wetland would sit in the bottom of this valley. And you'd expect to find V-shaped valleys, but we don't. And this is what inspired this theory. You would then have gullies forming in a certain part of the wetland. And then eventually, like it shows in this next image C, this gully would fill with sediment, forming an elevated depositional feature. And then this would repeat across the valley floor until you ended up with a U-shaped valley. And this is what's observed in reality. And so it seems that Palmiet Wetlands might have been formed through this process. At least this is the best theory that we have at present to explain why these wetlands form where they do and why the geomorphology looks like it does. So the next part of this talk is going to be based on some of my own research. And so I want to just show the study sites that I used for this research, and we'll do this through a video.
Well, it seems like we might have lost audio from Alana.
Hi, this is Tony. It looks like when we play these videos that it actually mutes the speaker. So Alana, if you want to unmute yourself here, apologize for that. This is a new feature of ours. We're still learning. Alana, you'll have to or unmute yourself there on GoToWebinar.
Is she able to do the unmute, or can you do it for her, Tony?
Yeah,
I couldn't do it myself. Okay, I'm back. Sorry, that's a bit of a pity. But this is the second wetland site, the Churchill wetland, and here we're looking at the degraded part of this wetland. You can see the trees on the left-hand side of that red square. That's alien invasion of the wetlands. This is the second pristine part of the Churchill wetland. The red that you see is bracken, serratum, and this is the upper part of the wetland that we consider a pristine site or least disturbed site as well. You can see, just like the Kloof, that this is in a mountainous region that becomes unconfined into this wetland system. So these systems tend to receive quite high rainfall from the mountains. The previous site that you saw was one of the highest rainfall regions in the country. Just those mountain ranges produce over 1,600 millimeters per annum, which is far higher than our average nationally. So moving from the Churchill Palmiet Wetland then to the last site, the Krom Palmiet Wetlands. Again, the green outline showing the least disturbed part that we chose to survey, and the red showing the degraded part. So this is the Palmiet peatland in the bottom of this valley. You can note the patchiness of the vegetation. This is it has much lower rainfall than the first wetland that was shown. It is about 700 millimeters per annum, and the lowest mean annual runoff of about 25 million cubic meters. This is the degraded stretch. You can see it looks quite different. There's a little bit of a wetland at the bottom end of that little wetland section. You can see the palmiet there, but the upper part is the alluvium is completely eroded away, and there's just sand left in that basin. This is the local town downstream, and even further downstream, this is the Churchill Dam, which is one of the very important water providing dams for the city of Port Elizabeth. You would have seen also with the Kloof wetland, it also occurs above the Kloof Dam, which is very important for the city of Cape Town's water supply. So these palmiet wetlands are very strategically located.
Alana, do you want me to replay the first minute so you can talk about that?
No, that's fine. The main point is just to show the three sites. That's fine. All right, so those were the three sites. Hopefully it just gave you a bit of an idea of the context of these wetlands and where they are located in these steep valley bottoms associated with these mountain ranges. Let's see if I can get the slides to advance. So at each of these palmiet wetlands, you could see that I selected degraded and pristine sections. And within these sections, I did cross sections through the wetlands as transects, and there were have I lost control? I think. Okay, well, so on this slide you can see these transects that I mentioned, cross sections through the wetland, and there were about 6 plots per transect, and the blue dots show the location of piezometers that we put into these wetlands. Okay, next please. Or do I have control? Okay, so just to briefly go through the methods, if you can probably just run through this slide quite quickly. But just that we had, there's 21 plots that I use in the results that I'll show next. I'm comparing the patches in the wetland of palmite dominated communities, which are defined as communities with more than 50% of this palmite plant, compared to fynbos communities, and that could be any of them just grouped together. And then in terms of sampling the vegetation, we did a full floristic inventory, identified dominant species, measured functional traits on these, measured biomass, as well as some other plant chemistry. Also measured various aspects of the soil chemistry, organic matter content, water content, bulk density, so many physical properties, and also groundwater. In the piezometers, we measured water level as well as water chemistry. There we go. And then also we measured microbes through the microbial biomass carbon index. In terms of analysis, we did a DCA and used linear mixed models in R. So in terms of wetland biogeochemistry, what do palmite wetlands look like? So the soil pH of the pristine parts of these palmite wetlands tends to be around 4.8, with a water pH of about 6.4 and groundwater EC of about 200. Soil bulk density is around 0.3, cation exchange capacity around 21, soil water content about 60%. I've already gone through organic matter and carbon. In terms of nutrients, soil phosphorus pools of around 102 milligrams per liter, soil iron of around 16,000 milligrams per kilogram, soil ammonium pool of around 1.6 milligrams per liter, and nitrate pool of around 0.16 milligrams per liter. So you can see there's huge variation associated with that, but it just gives you, if you're used to measuring these things in wetlands in your own countries, you can probably relate this a little bit. How does this relate to other wetlands in this region in South Africa? So wetlands in the southwestern Cape and wetlands that are valley bottom wetlands specifically. So the water pH tends to be a little lower than just all wetlands in the Western Cape, but a little higher than other valley bottom wetlands. And the groundwater EC is far higher. And probably it's an indicator that palmite wetlands tend to be more connected to the groundwater than these other wetlands. But there'd have to be more research done to show this. This is just to give a bit of local context. So that's the biochemistry. What about vegetation? What drives different plant communities? So as you saw the video playing, you perhaps noticed the patchiness of the color of the wetlands, and this represents these two different communities, the fynbos dominated ones and palmite dominated ones. So what's driving this patchiness? So we have here the palmite communities I've kind of outlined here in purple just to show you where the patches are, and two different fynbos communities given here in yellow. And this is the result of the study. The fynbos communities had a significantly higher pH of around 4.8 and around 4.3 in palmite communities. The water table was closer to the surface, significantly so for fynbos communities, and much lower for palmite ones. Palmite communities had a much higher vegetation cation concentration, whereas plant dissolved silicon was higher in fynbos communities. And in terms of the functional traits, community-weighted means of stem diameter, leaf length width ratio, and leaf area was higher in palmite communities than fynbos ones. Also leaf cellulose and lignin content. So just to show this also on an ordination, the same thing. Here we have all the fynbos communities in yellow and the palmit ones in green. You can see that there is some overlap, and that's probably because there's a bit of a continuum among communities, not just extremes in terms of we just chose the cutoff to be 50% dominated by palmit, but there's obviously a continuum here. And some of these key things I just want to point out, pH being significantly different, vegetation cations of potassium and magnesium higher for palmit communities, certain community weighted means higher in palmit communities, and dissolved silicon higher in fynbos communities. Okay, so we know that pH and water table is significantly different among these communities, but are they driving these communities, or are the communities determining these local conditions? And that's a question that is still not answered. So what else could be causing what else could be causing these differences, or the patchiness in these communities? So we could look at, for example, competition and disturbance, for example, fires or perhaps floods. So this could perhaps be a reason for palmit communities, or palmit-dominated communities having a thicker stem. Perhaps they are fire retardants. The vegetation potassium and magnesium concentration that was significantly higher in palmit communities relative to the fynbos ones, this difference is not reflected in the soil or groundwater. So it's not clear why this difference should occur, but the accumulation of potassium could be the result of high transpiration rates, which could also link to the lower groundwater table. Another possibility is that it's indicative of palmit communities being older than the fynbos ones. So perhaps the tissue concentrations reflect longer term uptake from the soil or groundwater, or flood pulses perhaps. And the overall larger stem diameter of palmit community could also be linked to being a fire retardant as opposed to a fire promoter, like the fynbos communities. The significantly higher leaf length width ratio, so the long strap-like leaves, could be an adaptation to the mechanical disturbance of floods. And the higher cellulose and lignin concentration of the leaves of the palmit communities, but lower biogenic silica concentration, could indicate higher stem flexibility, also linking back to flood adaptations. And we didn't measure below ground traits in this study, but other research has shown that clonality is really important, and rhizome internode length has been shown to be important in explaining vegetation patterns. So how all of this is important is it links to understanding how these palmit wetlands form. So as a result of this work, we've developed 3 theories of palmit vegetation dynamics. The first is autogenic succession towards fynbos communities, towards palmit communities. So fynbos communities would be the earlier successional stage. The evidence for this is the richer or the higher diversity in fynbos communities, which is characteristic of a pioneer stage, and palmit-dominated communities having higher potassium and magnesium, perhaps indicative of being older. And the assumptions here would be that fynbos species are superior juvenile competitors and have higher success at establishing from the potential seed pool. And secondly, that palmit is a superior adult competitor, able to take over by predominantly clonal growth. So here we have a cross-section showing 2 different communities, the palmit community and a fynbos one, this one showing its diversity. And the second graph is showing this, what I've just explained conceptually. So we have the Palmiet wetland represented by this rectangle, perhaps some local flood damage, ripping a patch out, perhaps a fire burning through the wetland, killing a patch, and over sort of geological timescales. So first fynbos colonizing in there, and then palmit taking over clonally from the sides and closing these up again, where in the meantime probably more disturbance would take place and this thing would continue. So that's the first theory. The second theory is that of fynbos communities being, So fynbos communities being the climax community, with palmite-dominated communities being pioneers. So following severe gully erosion, it's been noted that palmite establishes well in the gullies. So this is a patch of palmite that has established in a huge gully that is several meters deep. You can see it in the background, and it's kind of just clinging onto, like, surviving on the edge. So it's proposed that palmite traps sediments and organic material and expands in a patch until the wetland is raised, more sediment gets trapped, and the gully would then eventually be refilled. And that's shown in this conceptual diagram on the right, where you have an intact palmite wetland. A patch is ripped out, perhaps by a flood or through this gully erosion. The gully migrates upstream eventually. Palmite grows over this gully, it traps sediment, and then the gully So if
Okay. Are you back on, Alana? We're having some audio, at least I am having audio difficulty over the last slide. Perhaps you could go back and go over that again.
Okay, sorry about that. I didn't know that it had lost me.
They're just on the last slide.
Can you hear me now?
I can hear you now.
Okay. Sorry for all these technical problems. So I was just saying that the second theory is about autogenic succession towards fynbos. And evidence for this is that we have these palmite patches that form in gullies that have formed, where it's relatively inhospitable, no other species are able to colonize, and palmite is able to regrow. And the theory is that they would trap sediment over time and the patch would expand until they eventually close over the gully. The slide that's currently showing shows another example of this, except that it's not in a gully, it's at a dam, so there's open water, and palmite is colonizing. The first image at the bottom is from 2005, and at the top is 2018. And you can see that those patches have been expanding over that time. So that's the evidence for this. But the assumptions for this theory would be that palmite is a superior juvenile competitor, and that fynbos species would be able to outcompete palmite once it's reached its mature state. So through this, palmite transforms a habitat from one that is inhospitable to one that is ideal for another species. So it's acting as an ecosystem engineer. So the next theory, and the last one, is, I just want to see if I can advance the slide. I seem to have lost, I can't see the little controls at the bottom. All right. Okay, so this is a theory of non-directional maturity. In other words, that all communities may be mature communities and that there isn't any temporal succession towards a climax community. So the assumption here would be that both palmite and other fynbos species have equal or similar juvenile colonization abilities, but that depending on conditions or challenges to their environment, that would determine which establish. So the evidence for this is in this figure, where this is the Choko Palmiet Wetlands, and the black arrows show patches that seem lighter. And those patches are palmite patches. You can see it in the 2014 image at the bottom. You can see the colors standing out clearly. Then we have 1984 and 1954 at the top. And if you look at the extent of those patches over time, there's barely any change over 60 years. So it seems like these communities are they're not slowly changing. So perhaps it's possible that the expansion of palmite communities into fynbos or vice versa takes place on much greater timescales than can be captured by aerial photography. And if this is the case, then this has very important consequences for restoration and rehabilitation. And that's what I'll come back to this a little bit later. So just to conclude this section, many restoration programs seek to use palmite as a pioneer species. Do I have control? Oh, there you go. So many restoration programs seek to use palmeet as a pioneer species in replanting efforts on the basis that it's an ecosystem engineer and therefore would be able to colonize degraded stretches of a river or wetland. But this may not be the case. This is only the case in one of our two proposed theories. Palmeet seems to be reliant mainly on clonal growth for propagation. And this has critical implications for restoration activities. So firstly, perhaps palmeet may not be the best species to use for the initial stages of restoration. And secondly, if it is planted, it may experience better establishment and higher survival if it's planted in patches rather than individually. And we certainly need more research into this in the future. So the final section of this part of the talk is just on ecosystem services of palmeet wetlands. And I'm going to go quite fast over this just for the sake of time that we've lost with technical things, but the details you can find in these papers. And basically, I measured 3 different types of ecosystem services. These are the important ecosystem service complexes that have been highlighted to be important in wetlands in the literature. The first is carbon sequestration. And I measured this by measuring or calculating peat accumulation, which is just accumulation rates times the soil bulk density. Then carbon sequestration, where that is multiplied by the percentage of carbon. And carbon storage, where we then multiply through by the area of the wetlands in consideration. For water purification, we used a rather, I suppose, novel approach of trying to, it's almost like a water balance, looking at stretches of palmeet wetland and understanding what, in terms of nitrogen and phosphorus, is taken up over that stretch. And we repeated this over many sites, and we also did a smaller scale study to try and almost validate the results. And in terms of flood attenuation, we developed a flood flashiness index based on the relationship between rainfall and storm flow, and then applied this to some of the other catchments. So in both cases, we found it important to actually calculate water purification and not just water quality. And the same with flood attenuation. Really, what is the benefit of the ecosystem in producing this service and not just what is the force of the flood? And the results, just very quickly, for carbon sequestration, we found that palmeet wetlands sequester 0.33 tons of carbon per hectare per year, which is rather similar to, for example, Scottish peatlands. In terms of storage, storing around 550 tons per annum. And the key result that we found here was not so much that they're taking up huge amounts of carbon per year, but rather that accumulated carbon, if it's lost in a sudden event, like through erosion or after a flood as a result of degradation, that's where the huge impacts occur. So in terms of water purification, palmeet wetlands compared relatively well in terms of nitrogen uptake to other wetland systems, so slightly lower, about 222 kilograms per hectare per year, which is lower than some other studies, but it was tended to be much more efficient at phosphorus uptake compared to other studies. And flood reduction, we calculated to be around 61% for all of the wetlands combined. And just to say that this was for, if we looked at those last remaining patches of wetland in South Africa, these palmeet wetlands, which comes to about 16 kilometers squared. These are the services that are currently provided from these wetlands. So just to wrap up then, palmeet wetlands are in decline. We know this. We know that they provide important services to society. We know that there's a high potential for supply for these services. The wetlands are located above dams in many cases, so there's potential for incorporation into payments for ecosystem service schemes or similar. And in terms of recommendations, we recommend more strategic use of these wetlands, for example, where there's conflict between marginal agriculture and water provision. And then rehabilitation, do we block gullies or don't we? I'll come back to this briefly at the end, and this links to thresholds in valley bottom wetlands, and we need to research this further and see it from an ecosystem service perspective. All right, I have to move fast now because of all the technical things, but what is the impact of degradation on palmeet wetlands? And here I just want to explain the types of degradation we see in South Africa is really alien tree invasion, as shown in this image, accelerated erosion, like gully erosion, drainage, extraction, diversion. This is a farmer that illegally just put a channel in and berms to protect his orchards from the heavy force of floods, pollution, overgrazing, poor fire management, and climate change. In Palmiet Wetlands, there were two types of degradation we explicitly looked at. Firstly, gully erosion, and secondly, agriculture, so drainage, extraction, diversion, and so on. And the terminology I'll use here is pristine, but also degraded. And by pristine, I'm really just meaning reference or least disturbed. They are not entirely pristine, but it's just to keep the talk simple. And also degraded, there are different levels or degrees of degradation. So for example, for gully erosion, on the left here, we have an image of a channel that is eroding and peat is being lost. But on the right, it's an entire valley bottom that has, the alluvium has been washed out. So there's quite a significant difference in the degree of erosion here. And we included all of these in this particular site, so in this particular study. This is a picture of the erosion in the Krom wetlands. If it will go to the next slide. Seems I have a lag. So the next slide, when it does come, it shows a huge gully, which is about 200 meters across and several meters deep in the Krom wetland. And in terms of agricultural degradation, here, this image that I showed before with this channel that the farmer just built through the wetland, and also, of course, agricultural runoff. This is the Goko site. So you can see the wetland, I've outlined it in green. There's a gully that has formed in red, and then agricultural runoff coming into this wetland. And as a result of these combined factors, you also have invasion by alien trees. So just quickly to show the results here of what the impacts of degradation, of all of these types of degradation is. Sorry, the slides are very slow. So this is just a picture on the ground from what I just showed. But I'm just going to go quickly through the methods. It's exactly the same as before. It's the same fieldwork, but just now we're including 18 degraded sites as well. And the results show that degraded wetlands tend to have a higher soil pH than pristine ones. Also a higher EC, and all of these results I'm showing are the ones that are significant. So significantly higher EC. Okay. And also a significantly lower soil water content. So 21% instead of 60%. And significantly higher vegetation phosphorus and vegetation nitrogen relative to pristine wetlands. So the very interesting thing here is the increase in pH and increase in EC, and that's linked to, well, there's many reasons that could cause it, but also linked to increase in pH. Sorry, it's a result of fertilizers and lime applied by the
Alana, we've lost your audio again. On the slide with the degraded and pristine comparison. See if we can get Alana's audio back. I was hoping for what happened last time where we got her back on. Alana, if you can hear me, we still lost your audio. Are you there?
Kim, this is Tony. It might appear she might have lost her internet. GoToWebinar is reporting that she is offline, although it does show her still as a panelist.
Okay, we'll give her a couple minutes and explain to the audience that, yes, that she alerted us that they've been having times in South Africa when they're cutting the electricity because they run out of budget, I suppose. And so we were lucky that at this point we just had one little blip, and so unfortunately I think maybe her internet has stopped. However, I think she was going to try to call in on the phone if she can, and we'll just give her a couple of minutes. I do, while we're doing this, maybe we could advance slides to the announcements, and then we'll go back if we get her back on. Can you go ahead and do that, Tony? I think we have quite a few slides to click through there.
Can you hear me?
Oh, you're back.
Oh, you're back. Excellent. Okay,
I'm not sure what happened. Okay, I still have an internet connection, so I'm really not sure.
Okay, because Tony thought that maybe your internet connection was cut. So I think he's trying to get back now where we left off.
All right, well, I'll just quickly keep talking so that we don't run out of time. What was the last slide that you heard?
You were comparing the degraded and pristine sites with soil pH and those types of things.
Okay, so basically,
Tony's got us.
Yeah, great. So the main difference here was significantly higher soil pH for degraded sites compared to pristine ones, and significantly higher EC. And there were some differences that were only apparent for the Choko and Crom wetlands, and the reason for this, let's see if I can get it going, was that these were the only sites impacted by agriculture. So the results we see now are those that are significantly different between sites that are pristine and those degraded by agriculture and gully erosion. And this was that there was a significantly higher soil bulk density on degraded sites, significantly lower cation exchange capacity, significantly lower soil cations of various kinds. So just perhaps to move on from here. I'm going to just skip the ordination because we're completely out of time, but just basically highlighting the variation in these sites. And then also I have a series of graphs which show each of the sites and for each variable, but I'm just going to skip that. If you're interested, you can have a look at the slides afterwards, just if you want to understand the variation in these parameters for some of the sites. One thing that was perhaps interesting was that soil cations tended to be higher for in the soil, base cations for pristine sites relative to degraded ones, but this was completely the opposite in the groundwater, where cations were much higher in the groundwater of degraded sites. So the reason for this is probably because there's some leaching. And then lastly, it was also higher in the vegetation. So for just looking at cations, how that varied between soil, groundwater, and vegetation. Okay, so just to wrap up this section, then basically the main impacts of degradation was a loss of soil organic matter, a loss of alluvium, and a reduction in soil cation exchange capacity and bulk density. And these all affect the ecosystem services that I mentioned earlier. Lastly, I just wanted to quickly go through some of these different restoration strategies that we use in Palmiet Wetlands. So I'll just go quickly through this. So just some definitions. By restoration, we really mean repairing to a reference condition. Rehabilitation is restoring some level of function. So in terms of wetland rehabilitation, we use gabions and weirs. Gabions being these concrete structures to supposedly solve the impacts of gully erosion. Here on the right, you can see one of these structures and one in the foreground that failed because the engineers underestimated the force of this system. And you can see the Palmiet wetland recovering behind this weir. In the next slide, let's see if it... So there are some other negative consequences of these structures, and this is largely that erosion downstream of these sites increases, downstream of these weirs increases dramatically, whereas it prevents upstream migration of the gully. So this is the weir, and you can see the intact peat basin behind the weir, and downstream how the system has become incredibly channelized. And just to show what the cause of this was, this is the wetland in 1954. You can see the peat beds really fill the valley bottom. And here at the bottom, you can note this road. And if you look at the same system 60 years later or more, you can see that this entire peat bed has been lost. And it was the result of this road. I met the farmer who said he used to drive over that road 40 years ago. Okay, so then other types of restoration includes alien clearing. Okay, so this was just what I was saying, is how effective is this rehabilitation really? Okay, so other restoration techniques are alien clearing. So this is clearing invasive alien trees. We have various strategies for this, but the one way is mechanical clearing. So this is an example by hand using chainsaws where teams go in. And this is an example of, wow, okay, an example of where heavy machinery goes in to do the clearing. And then there's also an example of pesticides that we use in certain cases where there's coppicing. And lastly, also biocontrol. And then we've got prescribed burns, and we often try to use this because these systems are fire adapted, but then there really needs to be clearing right after the burns to control the seedlings that come up. This is a controlled burn happening in a palmiet wetland. Okay, the biological control that I mentioned. And we have many other techniques like revegetation, re-wetting, livestock exclusion, education and societal behavior change, but we don't really, haven't really used that in palmiet wetlands. So in South Africa, we have some room for improvement. Our efforts tend to be patchy and small scaled, and we don't really monitor our effectiveness very well. But positive aspects, we use restoration to do job creation, and we also have many value-added industries that we explore alongside that. So just to conclude, palmiet wetlands are unique peatlands globally, located in high energy, steep valley bottoms, highly connected to the river network, in areas with high evapotranspiration and low rainfall. They're possibly formed through localized erosion leading to valley floor planing, and there are 3 possible theories for palmiet community assembly that are proposed, and we need further research on this. They provide valuable ecosystem services and should be strategically preserved. And degradation leads to a loss of alluvium, soil organic matter, reduction in cation exchange capacity and bulk density, with an associated loss of ecosystem services. And main rehabilitation efforts consist of blocking headward gully erosion and clearing of invasive alien trees, but we have major knowledge gaps here. And the result is that there's great opportunities for future research. So with that, apologies for all the technical problems. Phoning in from South Africa is not without its challenges, but I'd just like to say thank you very much for your time and for your attention.
Thank you so much, Alana, and I think we should apologize for some of that, interruptions. It's the system that relies heavily on the internet, and we always have some difficulties here and there. So we just have a couple minutes left, so I do want to get to some question and answers. Before I do that, I want to point out that I am really kind of surprised at the analogous situation you have there as we do in South Florida. Now, we don't have the any kind of relief, topographic relief whatsoever, so we don't usually have the gully wash. As far as the plant species and the invasive trees, we have that type of situation. We have fire adapted systems, and we are using a lot of the same things that you talked about for restoring some of the areas that have either been impacted by agriculture or have been impacted by fragmentation, and we don't have the fires that we used to or the hydrology that we used to. So we use mechanical clearing and herbicides, and we don't usually do anything by hand because the areas that we're working on are quite large. But the native species in the Everglades is sawgrass, Cladium gemescens, and it's very similar to some of the things that you were talking about with the palmite, with thick stems and a sort of clumped clonal expansion and things like that. So it's very interesting, some of the things that are very similar with different species. We also have invasion of a tree species that is a native, which is Carolina willow. And so we see these kind of real bunchy, like tall grasses or sedges being replaced by shrub systems. And so that's something that's very interesting, analogous, that would be really interesting to find out. And I also want to find out about your flood flashiness index, because I'm really interested in finding out about that. Do you have any comments about that? Have you heard about some of the things that we are dealing with in Florida and other places with these types of, same type of successional invasions?
I actually haven't, so I'd be very interested to look into that further. We tend to really focus on other similar Mediterranean type systems in our comparisons, so it's great to hear about it. Thank you.
Good. All right. Well, I want to ask a question that one of our participants asked. How are the activities in or near these wetlands regulated? What is the situation on regulations in South Africa?
Thanks so much for that question. It's a really good one. We have, I think, one of the best water laws globally. It's very sophisticated. It's one of few that recognizes the environment as one of the only rightful users to water. So the environment and domestic use are the only two legal rights to, they're the only ones that have a right to water. So industry and agriculture and all the rest come next. But our biggest problem is regulating this. So there's very little regulation, and with the result, people pretty much do what they want. And it's the same with our laws governing wetlands. We've got many laws that state that people need to maintain buffer zones, which are defined as 20 meters from the boundary of the wetland itself or river system. And again, unfortunately, that's not enforced. And then, of course, you've got issues with most of the damage was really done in the 1980s. My research has shown anyway, and some perhaps before even aerial photographs were taken, which was like the 50s for us. And so you can't, in South Africa, we don't have any kind of way to deal with things that were done in the past.
Right.
So people are then encouraged to, retract the wetlands, but not there's no law to enforce that.
Right. And I think enforcement seems to be the issue in a lot of places, not just in South Africa, I think.
Absolutely.
I have a question. One of the things I was thinking about is, one, I wanted to know what the invasive tree species were, and I think I saw acacia and eucalyptus. Is that correct?
That's correct, yeah.
Okay.
That's our major ones.
I think we were going fast over that part, and I was like, I need to find out what those tree species are.
Yeah.
And then I guess both of those are from Australia, right? You said you had something from Europe that was invasive tree?
Yeah, pine trees. They're more of a problem in our mountain. Yeah.
Okay. Also, I want to ask about these systems, like what kind of animals use these, and how would they be maybe part where you were talking about how did these develop, the three different successional theories. Do any fauna of these areas, because that's some thick vegetation, and I know in our systems a lot of times we talk about having to burn it so that it opens it up for different animals to use it, especially with regard to sawgrass. So how do the faunal communities in these systems compare? Are there unique species that are endemic, and how they might have helped, maybe it's a chicken and the egg thing, but how they might have helped these ecosystems develop?
Well, I guess the short answer in terms of the succession of faunal communities is that I have no idea. I don't think anyone has looked into it. In terms of fauna, there are some very interesting endemic species. We have an endemic redfin fish. There are spiders in there that no one has even started to identify. So if people are looking for species to ID, it's a very good system. But yeah, certainly, you know, these systems are adapted to fire, but they would have been, the fire would have been far less frequent than on the mountains, especially when in the parts of the, you know, during wet seasons and so on, and during very wet years, it wouldn't burn. So I would expect them to have a fire return interval of that's far shorter. So with the results, I don't think that, yeah, I suppose animals would, you know, probably use it as a refuge during fires and then maybe move out after fires. I don't really know.
So what would you say the return frequency is for the mountainous areas as opposed to this area?
So in our fynbos mountain systems, the return interval could be between 8 and 25 years, depending on the type of fynbos. So some fynbos needs to burn more regularly and some less frequently. As for the Palmiet Wetlands, we have absolutely no idea. So like I said, probably when they're relatively healthy, they would almost always be wet because the systems are able to retain water in the dry season in most cases, except for extreme years. Whereas now when they've become degraded, I'd expect fire to be able to get into the wetlands much more regularly because the soils are dry and the vegetation perhaps a little bit more dry. So maybe, I don't know, at a guess, maybe once every 100 years or something, but it's a total guess.
Oh, wow. Okay, so when you were saying fire adapted, I'm thinking like ours, where, for instance, the sawgrass wetlands would be like every 3 to 5 years it will burn.
Yeah. No, they're very different.
So it may not be as wet too.
Yeah. Yeah.
Well, we also are like the lightning capital of the world, or at least the nation. So we have a lot of lightning strikes.
Wow.
Well, Alana, I want to just give you one last chance if you wanted to just give us one little bit of information you wanted us to take away with us, or if you wanted to just kind of recap. I'm going to just give you a minute to do that before I make our lead out announcements.
Thank you very much. No, it's a great opportunity. I'm sorry for the technical difficulties. Thanks again to those who took the time to listen. And just to say, I mean, there's so much still to be discovered in these wetland systems. So if you're interested to do some research, please get in contact with me or just come out and explore the systems. They're really quite spectacular and relatively unexplored.
Excellent. I think I want to come. I'll come and help out. I do some of that work, walk on top of the Palmiet Wetlands.
We would love to have you.
That's excellent. Well, thank you so much, Alana, for taking the time. I know you did a lot of time to prepare this, and I think that you had a great demeanor and resilience in being able to deal with the technical issues. So I thank you for that, and even in the audience too as well. I'm going to go ahead and make our announcement. Let me see if I do have control. All right. Oops. Our next webinar is going to be the second in our Spanish webinar series, and that's going to be next week on the 27th. And Dr. Casco is going to be presenting on the influence of flood pulsing in these areas. So I hope that you will be able to join us for that. Sorry I couldn't deliver that announcement in Spanish, but I don't speak Spanish, so I won't even know what she's saying until I watch it on the YouTube channel where I can get some captioning. And then after that, we have the March 14th SWS webinar. It will be our regular SWS webinar series, and we have Professors Bill Muma, who works in climate type situations, and Max Finlinson, our SWS president-elect, who will be giving the webinar on March 14th. It will be later than our normal time. It's also going to be on a Thursday. It'll be at 3 p.m. Eastern time. So I hope you will be able to tune in for that, and make sure you tell everybody you know to come, because they're going to be talking about wetlands and changing climate. And it will be, I think they'll be very well attended. So please make sure you tell everyone to come. It's free for the public, so they can come out to that one, as well as the Spanish webinars. If you speak Spanish, they are also open to the public at this point in time. So with that, I want to thank, again, Alana, for your presentation today. I also want to thank Tony of SWS staff for helping us in and out with the technical aspects of doing the webinars. And also want to thank you, the audience, for participating today. So everyone have a wonderful day, and we will talk to you next week sometime if you come to the Spanish webinar or next month. Thank you and goodbye.